Video? Oh, yeah.
The video has started. That's exactly right. This is the Atomic Trivia War 9000. I'm your host, Jason Hawk. Let's meet our contestants from San Jose, Costa Rica. That's how you pronounce it, right?
Yeah, sure. Whatever.
Let's give our big welcome to the artist that is the smartest, Omar Hernandez. And from Toronto, Canada, I want to hear it for our very own Papa Bear, Kevin Archibald.
The artist formerly known as Papa Bear.
Joining us this afternoon and this evening, since he's in a time zone set in the far-flung future, our very special guest, a physicist who can explain why radioactive cats have 18 half-lives. From Finland, our friend Timo Ruppell.
Hola, mis amigos.
And he speaks Spanish better than Omar does.
Well, I will give you that this thing is now like at least 500% more smart.
More smart, yes, not smarter. No wrote today because she apparently thinks that family is more important than trivia. So it's just a big sausage fest here. It's us four dudes. Let's open with a joke. Two hydrogen atoms met at a bar. One said, "What's wrong, buddy?" The other responded, "I lost an electron." The first atom said, "Are you sure?" The other replied,
I'm positive.
"You got it." Sorry, had to bring the Trivix jokes. The Trivix
that was
trivia physics.
Painful.
Such bad.
You know, we're going to be focusing an awful lot on the physics today, and that's because it's not often that we have someone that actually understands them and can correct us when we get them horribly, horribly wrong. So today's show is actually divided into two parts. First, we're going to have a physics trivia free-for-all.
Basically, what you're saying is you're inviting a gynecologist to talk about vaginas. That's it, right?
That's exactly it.
The thing he does every single day, the thing he works with every single day, this is his time to loosen up a little bit, and you bring physics.
Indeed.
You're such a special guy.
But listen, there's two parts. The first one is all about physics, and the second one is like pop culture stuff.
Okay.
Oh,
Okay.
You're going down. Pop culture, son.
So here's what's going to happen. We've got 10 questions in the physics trivia free-for-all. Anyone can answer these. They're not for any one given specific person, but you have to let me finish the question before you go ahead and answer. So, question number 1. Everybody ready? Everyone set?
Boom.
Timo, you feeling good? You feeling confident here?
I'm feeling up for the task. Come on.
Excellent. Every particle of matter has a corresponding particle with identical mass and spin, but an opposite charge. What are those corresponding particles called?
Antimatter. Come
Timo
on.
gets it.
Tip of my tongue.
Should I give you like a 5-second lead time for everybody else? Oh.
Smack talk.
No,
I like it.
that way will make you'll just make us look dumber.
Number
Now we
2.
can say, I knew.
Number 2, this German theoretical physicist is considered the father of quantum theory, winning the Nobel Prize in 1918 and promoting widespread adoption of Einstein's special theory of relativity in Germany.
Wow.
You don't need to give us 5 seconds, Timo.
Yeah, but that's physics history. That's like the boring stuff. Schrödinger?
No.
No.
Wow.
Oppenheimer.
German theoretical physicist, father of quantum theory, Nobel Prize 1918,
Pauli?
Max Planck.
Planck. Okay. One of those guys.
Number 3, in particle physics, this theory states that at high energy, the 3-gauge interactions of the Standard Model, which define the electromagnetic, weak, and strong interactions or forces, are merged into one single force.
What, this theory? Are you asking for the name of the theory?
This theory, yes, the name of the
Grand
theory.
Unified Theory?
And Timo has it again.
Not the menage a trois theory.
This is, I mean, I'm suspicious of the level of sophistication of these questions. I mean,
No, they're for everyone, they're entry level.
okay, excellent, yes.
Of course.
Number 4.
So
This
wait,
is
just to clarify, the reason that you hesitate so much is they're so easy that you assume there's a trick involved.
Yes. I'm also Googling for YouTube links to send you so you can entertain yourself while I'm taking these.
Wow, that just happened.
Number 4. This is an unstable elementary particle similar to the electron, with unitary negative electric charge of -1 and a spin of 1/2, but with a mass about 200 times greater.
Quark.
No.
Then the electron?
Yes.
And 200 times?
About 200 times greater than the electron.
The proton?
Ion.
But that's way more. That's 2,000 times more
Now,
heavy.
see, this is the danger of physics questions, because I don't know enough about physics. I'm like an elephant in a china shop here. I can get in there, I can try to make questions.
Wait. Unstable. Yes. Okay. Sorry. Muon? You're looking for the muon. Yes.
Muon is correct. There we
Got
go.
confused a little
You
bit.
had me really nervous. I thought that I was way off.
No. You're correct.
Okay.
200 is way. I mean, that's way off, right? It's not. It's like, if I remember correctly, it's like 170 something.
Yeah, 200, man. Come on, yeah. Oh.
Number 5. A man has a mass of 200 kilograms on Earth. What would his mass be on the moon?
200 kilograms.
Exactly! Nice!
Oh, my.
Kevin gets one.
Of course.
Number 6. Represented by the lowercase letter v, this subatomic particle is electrically neutral, meaning it does not carry a charge. It has a half-integer spin and is created in the hearts of stars, such as our own Sol.
It is not a V, it is a Greek letter mu for nu for neutrinos.
There you are. See, I was trying to cater to them. They wouldn't have known what a nu was.
Might have given them a hint, though. Neutrinos.
No.
Number 7.
No, it wouldn't have worked.
Number 7, caused by relative motion toward an observer. Toward an observer, as described in the Doppler effect. This colorful term is the decrease in the wavelength of visible and non-visible light alike.
Oh, yeah. Blue shift.
Blue shift is the answer.
And there was a
It's
trick,
opposite
because
being
normally
red.
you call it red shift, but that's away from the observer.
Exactly. And it would be
Oh.
an increase in the wavelength.
Okay, now that Half-Life expansion pack, Blue Shift, makes so much more sense.
Yes,
See?
it does.
I
Number
thought
8.
it was blue shift because the uniformers were
Yeah,
blue.
it is, but it's obviously a double play on words, which
Hmm.
now, 15 years later, we're now getting.
Finally get it.
Jason is here to help you.
That's right. Number 8. You've most likely heard the name because of its work with the Large Hadron Collider, and because Timo has some affiliation with it. But what does CERN stand for?
Something, smarty pants, something.
CERN. C-E-R-N. It's a trick question, by the way.
No, it's not a trick question. It's
CERN
just that
means
the answer is in French. So it's Centre Européen de la Recherche Nucléaire,
Ooh.
European Council for Nuclear Research. Exactly right.
or Conseil au Centre. Anyway, yeah.
It sounds suspicious being French.
Yes, it is. Everything French is suspicious, eh?
There's the bell, by the way. Number 9. First put forward, and I'm not sure if this is Edward Witten or Edward Witten, but first put forward by Edward Witten in 1995. This theory unifies all consistent versions of superstring theory, which incorporates fermions and supersymmetry.
55?
1995.
95. M theory.
M theory is correct. All right,
Are
number
you
10.
having
I'm
fun?
highly suspicious that this barrage of questions is so that I have some chance of competing with you on points in the pop culture portion.
No,
of
this barrage
quiz.
of questions is designed to show our listeners just how stupid our regular contestants are.
I'm beginning to feel like Ro on a regular show.
We'll end things with an easy one here. This is the final physics question, number 10. If the principal quantum number of an electron is n equals 4, how many possible values of the orbital magnetic quantum number ml are there for this electron?
8.
N equals 4. And you want to know... Wait. N or M equals 4?
N as in neutrino.
N as in neutrino equals 4.
How
And
many
you want to-
possible values of the orbital magnetic quantum number ml are there for this electron?
Crap.
4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18,
Spam the
19,
mic.
20.
Spam the mic.
Squared minus 2, 15, maybe 15.
Actually, I'm going to give this point to Omar. because his first guess was 7. Or I'm sorry, his first guess was 8, and he was only off by 1. It was 7. 7.
Yes!
Yep. Okay, so I promised Timo last time that he was on the show that I'd have him on for regular geek trivia, not physics. So here goes. We'll just do basic pop culture stuff. Here we are. Number 1.
Again?
Free for all again.
Okay.
Question number 1. Often invoked in Star Trek, such as using streams of them to disrupt other ships' shields. This is a hypothetical particle that always moves faster than the speed of light, Jordy.
Phaser?
Tachyon.
Tachyon. See, it's just pop culture stuff. No physics.
Yes. I see where this is going.
Yep.
Front row, Shaggy.
Number 2. Tom Cruise and Dougray Scott race at each other on motorcycles, leap, and then collide in midair with a force of an estimated 124,000 newtons, according to Popular Science, in this 2000 John Woo movie.
Mission Impossible.
Impossible 2.
Kevin gets it. It's the Deuce.
John Woo.
They both get up and continue fighting, even though they should both be reduced to their basic particle states by the force of that collision.
See, with this question, you completely distracted me by talking about newtons, and then I just didn't pay attention after that.
I know.
No metric on your ass.
Yep. Number 3. Set in the year 2517, but released to TV in 2002, this series about a spaceship crewed by misfits bucked science fiction norms by accurately portraying outer space scenes without sound.
Firefly.
Firefly is the correct answer. Serenity, by the way, screwed that up. When it went to the big screen, all of a sudden, sound in space.
Yeah, that sucked.
Number 4. Asteroids do not have fault lines, no matter what Michael Bay tried to pull in this physics offender from 1998.
Armageddon.
Armageddon is the correct answer. Number 5. Walter Matthau plays Albert Einstein and waxes wise about Occam's razor in this 1994 comedy that romantically pairs Tim Robbins and Meg Ryan.
IQ.
Omar has IQ.
Nicely done. Omar, you always clean up with these romantic comedies, which kind of...
I like them. I like rom-coms.
It's not a bad movie.
I am not ashamed. I like them.
I'm with you there,
quasi-
Omar. I just watched the finale of Office right now, so...
There you go.
Is that the UK one or the US one?
The US one. The US one.
Okay.
What happened, by the way? I checked out sometime around season 5.
Oh, you should watch it. You should watch it.
So it doesn't decline in quality?
Well, there may be a tiny dip in between, but it keeps on being excellent.
Basically, once
I
Michael
rate it.
left.
Michael leaves at... When does he leave? In season 7 or something?
Oh, that late, huh?
Yeah.
Okay.
But it's still good. It's still good.
It is
Fair
finished
enough.
scientist approved.
Yep.
Number 6, on CBS's Big Bang Theory, this well-known physicist apologizes to Sheldon Cooper for, quote, the role I played in the Pluto affair.
What's his name?
Brian Cox?
No, it's not Brian Cox. Although his name is fun to say.
What's his name? You know.
Michio Kaku? I'm just...
Voice box and wheelchair?
No, it's not him either.
Okay.
He has nothing to do with planetary science. You
Neil
fool.
deGrasse Tyson.
Okay.
I was going to say Neil deGrasse, but I didn't remember that.
No offense to Timo, but if we had Neil deGrasse Tyson on the show, that would be something. We could actually have the two of you duel to the death. It would be
Oh, no.
like a
I would
cage
lose.
match.
I would lose.
It's completely different sciences, I think, right?
Yeah,
Well,
pretty much.
we would go pure pop culture at that point.
Yeah.
Yeah, we would be like, okay, how much do you two know about the Smurfs? Go. Number
Blue.
Number 7. This actor also wrote and directed the 1988 film Young Einstein, which made the physicist Australian and supposed that he split the atom with a chisel.
Yahoo Serious?
Yahoo Serious is the answer.
Wow.
He also later famously tried to sue Yahoo, the web company.
Really?
Yeah, he lost. He
course
really
he did.
lost. Yeah. Number 8. Nearly every episode of this television series, which ran from 1989 to 1993, started and ended with the time-traveling Dr. Sam Beckett muttering, "Oh boy."
Quantum Leap?
Yes.
Omar with the quick lips. Good job, sir. Number 9. Main character Quinn in the sci-fi show Sliders has a cat named this, after the physicist who memorably illustrated the Copenhagen problem of quantum physics applied to everyday objects.
Schrödinger.
Now with the Schrödinger, that's right. You all three get the point on that one. Number 10, a difficult one, considering that Kevin hates anime and that Ro is not here. Omar probably has the best shot at getting this question right. Timo, I'm not sure how much you like the anime. This important English physicist was the main villain of the 1996 anime The Vision of Escaflowne, who after 200 years went by the name Emperor Dornkirk.
Didn't like the series,
English
so I
physicist.
don't know.
English physicist. Newton.
Isaac Newton.
Nice.
He was
There
supposed
you
to
go.
be an aged Isaac Newton.
Hmm.
There we are. So all in all, I think that Timo won.
Yeah,
You
pretty
were
much.
keeping score, were you, Jason? You
It's
forgot.
appropriate.
Ooh.
But we wanted to have Timo on the show to talk about a couple different things. First of all, I've been wanting to have you on the show for quite a few months here because back in March there was this huge announcement that came out of a Harvard research study. They found the first direct proof of cosmic inflation right after the Big Bang, another important piece of evidence for that model. I was hoping that you could explain to us, first of all, what the Big Bang Theory is from a scientific perspective and not a pop culture perspective, because I think that there's a lot of misconceptions out there, and why this finding is important to overall understanding what the universe is and how it came about. Just a small
A small
assignment.
like 5-minute thing.
No, 5,000 words.
Yeah. So the idea of the Big Bang comes from the fact that when we look at space with telescopes and radio telescopes, we observe a couple of different things. We observe that things are moving away from us. The farther they are from us, they're moving faster, which sort of implies that everything is expanding. And then we are observing this sort of uniform radio noise which permeates everything.
You've already confused me, Timo, because here's what I'm thinking. The further that things get away from us, the faster they go. Isn't that exactly the opposite of entropy?
I think you're not understanding entropy correctly now. But yeah, there's a problem with entropy, but it's not that. Now, from these two things, we can conclude one sort of major phenomenological fact, which is that if you wind time back, then everything should be coming closer to each other, and this sort of uniform noise, radio waves, which permeates everything, should get warmer and hotter, and so what we think is happened at the sort of start of time is that there was a huge explosion which took place everywhere in space, and you can actually sort of do the math and figure out when this happened, and something like 13.7 billion years ago, and the problem, and this is basically the Big Bang theory. So there was a Big Bang, and after that, everything sort of expanded outwards, and we are now just witnessing the sort of empirical facts of this big explosion and the aftermath of that. The problem with that is that if you do the math correctly and the physics correctly, what we should be seeing in the universe should be much more messed up than what it is right now. Basically, we should be seeing, huge blobs of sky where the radio noise that we hear is much louder or much a different pitch, a different temperature, and what we are basically seeing is way too smooth to have come from this sort of explosion just a mere sort of 13 billion years ago. And that is where the idea of inflation comes in, which is that the idea is that sort of right at the beginning of the explosion, when the universe was microscopically tiny still, there was a period of extreme inflation, extreme expansion, so that things got blown up way faster and way bigger scale than we can imagine right now, and this sort of smoothed out all the bumps in the universe. All this sort of, if you think about the universe having lots of quantum noise or like a fireball, and that is basically why everything is smooth. So that's the theory of inflation. I hope this sort of did this justice, or made you understand it a little bit at least.
Can you make some sort
Tiny
of pudding
little-
metaphor, like rice pudding, or it would help if you could make us some sort of food metaphor at this point.
Food metaphor.
It's pretty clear.
Yeah, and so the thing is that during inflation we can basically model the things that happen in the universe. We can. What you do is you assume that the beginning of the universe is sort of like a quantum chaotic mess, and you look at what the equations tell you happens to that when it expands rapidly during inflation. And one thing that should happen is that when light scatters off gravitational potentials or gravitational bumps, or in this messy expanding thing, the polarization of light should get twisted in a certain way. And this twist is what they actually observed, or think they have observed, in March. So that is why it was a big news. It's the first sort of direct observation of the possibility of our model being correct for inflation.
Everyone, of course, that has problems understanding science or doesn't understand the scientific method says this happened in such a far distant past, it can't be observed, therefore it can't be verified. But what does this model do to address that question? I'm straying away from saying that certain segments of the population are asking that question, or certain affiliations ask that question.
Well, that's the main problem of science at a deep philosophical level, is the question whether empirical science can actually prove anything, and that's I think a more philosophical issue. Other than saying that if you open a door like 500 times, you're pretty sure you know how to open a door, and basically with science like this, we are pretty adept nowadays at looking at data that we gather from telescopes and particle accelerators and colliders, etc., and then doing math and physics with them and figuring stuff out. The whole process is obviously extremely convoluted and complex, and that's why you need a big education and a long education to actually do this stuff. And it is a real problem, because in the end you end up with people not believing you when you say that the climate is going to change and that human beings are pretty much responsible for it. But what you can do? It's a tough problem.
If everything in the universe is still moving away from each other, if we can still see things moving away from us, can we observe in any way still cosmic inflation at this point, or is it a force that's dissipated?
No, it's so cosmic inflation is not something that is a force. It's just the statement that things are accelerating at an accelerating pace away from us. And,
it's more like, is it more like you see a house destroyed, and you can tell a bomb went off inside the house? You didn't have to see the explosion, but according to what you're seeing around, like the scraps everywhere, you know that a bomb went off there.
It's more like you get there like a few milliseconds after the bomb goes off, and you're in like this matrix-like state where you see everything moving out in slow motion. That's what we are at in the universe right now. So you can definitely figure out that there's like a explosion happened.
That's the same reason why stuff is still accelerating away from us, and it's not slowing down.
that's a different story because well, actually, if you're really pedantic about it, then we are actually right now in an inflationary state of the universe. If we look at how fast things are going away from us and then look a little bit later at how fast they're going away from us, then the speed at which they're going away from us is accelerating. So we are right now in a state where the things are perpetually getting away from us with increasing
How can they be going
hard.
faster? How can they be going faster if no energy is being added to them?
Well, they're going faster because there's actually new bits of space being inserted between us and them.
Ah, it's the insert key.
That's
Someone's using like Control V. Someone's got Control C
exactly,
and Control V.
and is
Okay.
hitting it. It's that's
They're
the
just
thing.
leaning on that Control V key.
Exactly.
Okay.
And I mean the thing is that it is a tiny amount. It is so little space being added to us that the galaxy we're living in is not getting bigger. We're not even increasing the distance between us and the neighboring galaxies or the neighboring galactic cluster. What is happening with the space expansion is at a much, much larger scale. And when you look at, cosmologists do these simulations of what the cosmos is behaving like. What they basically take at the smallest single point in their simulations are individual galaxies. Because it doesn't make sense to model anything smaller in cosmology when you're talking about the structure of space or how it behaves.
No, I guess it's kind of like someone as low. I mean, not poor, but someone that doesn't have like a lot of money. You say like $2 billion, and you can't really imagine how much money that really is.
I mean,
It's
I
kind
can't
of that
imagine
kind of
how
scale,
much
right?
money that is, right?
Yeah. So it's that kind of scale, right? It's so
It is.
big that you have no idea how. I mean, it can't fit in your head just how big it is.
Exactly. And I mean that's part of the training that you get as a physicist is learning how to deal with these numbers. I mean, some professions have that. Like if you go into finance, then you're starting to be pretty okay with big numbers, especially if you go into government finance.
So what is it exactly that gave rise to inflation?
Uh,
Poor
rise to
economic
inflation.
choices, I think, it's right.
Okay, so Einstein came up with this theory of general relativity, and that is basically a theory that the simplest way to explain it is that Einstein figured out that instead of looking at gravity as a force between sort of particles, what you should think about is as energy and mass distorting space, and space distortions telling energy and mass how to move.
A big
So
blanket with the planets rolling around causing dimples
exactly
in
the rubber
blanket.
thingy where that's sort of a two-dimensional abstraction of it, but it is a really good metaphor. Well, it's a good metaphor for seeing how gravity affects the motion of other particles. But the deeper idea behind it is that the structure of space is determined by the content of what's in the space. And when you look at how, and so then you can start out what happens when you have basically all of space is a gigantic fireball. And you can ask what do the Einstein equations tell us? And then you can ask, what do the Einstein equations tell us when basically all of space is filled with like a hot plasma, or when all of space is filled by nothing but emptiness? And so you can basically evolve the universe, and that's what cosmologists do. They look at how the universe has evolved, and right now the equation is going from a sort of matter-dominated universe. And by right now, I mean it's like in this range of a few billion years plus or minus. But we are going into a period of the universe where it is going to be more and more, I think, radiation dominated. No, vacuum energy dominated. Sorry, vacuum energy dominated, which means that if you take an arbitrary amount of space and look at what is actually in this cube of space, you're going to find a little bit of matter, you're going to find some photons or radiation, and then there's going to be like the energy of actually having nothing in there, the vacuum. And with the universe expanding, what's going to happen is that the matter content is going to thin out, and the radiation content is going to thin out, and what you're going to be left is more and more of the sort of energy budget is going to be dominated by just the energy of the vacuum. And the equations tell you that when that happens, when you have nothing but vacuum inside space, then space will acceleratingly increase in size. That's what the equations tell you.
What about deflation? Will deflation ever be a problem?
Well, that depends on the sort of global aspects of the universe, and that's a big question of whether we have enough gravitational matter or to actually pull all of this back together again.
Because I know that the popular conception is that the universe has been expanding and contracting and expanding and contracting for time without end.
That is one possible idea that you can have. Yes, it is. It's interesting to see whether you can actually figure this out by looking at stuff like the Big Bang or stuff like the polarization of the light from the Big Bang. And yeah, there was a paper like last week by some Japanese guys, I think, who did exactly this. They tried to explain the results that the BICEP group had, and mainly their dispute with the Planck group by saying that maybe this is not just normal inflation, maybe this is like a hint of seeing something like the universe bouncing back from a previous deflation area. Yeah, but that's an open question, and currently it looks like the universe has just enough mass to, at some indefinite point in the future, to stop the expansion, but not start to deflate. Yeah, and that is a really interesting question because experimentally the value we're looking for is there's a number and it has to be 1, and it's really, really, really close to 1. And so you start asking yourself, maybe it is exactly 1. And what does that mean, right? Because that nature doesn't do exact numbers. If you look at pi or the charge of an electron or the gravitational constant, nothing is ever a whole number. So if we measure something and it turns out to be a whole number, then we theoretical physicists start getting antsy and want to figure out some equation or some way to explain this as it has to be exactly 1, right?
So the other thing that you just happened to bring up, and I think it was as a joke because I screwed up a date in our emails back and forth. You said that you would talk about imaginary time, and I haven't been able to stop thinking about this ever since. What is imaginary time?
Does it involve Doctor Who?
Is it time? Just time?
I don't think it. Imaginary time is just you can have theories where you have. So okay. Let's go. You know that we have 3 space dimensions, right? And then we have 1 time-like dimension.
Okay.
And so that's why we talk about 4-dimensional space. But whereas you can go forward, backwards, up, down, left, right, and you can come back to the same point in space where you've been before, and nothing's wrong about that, you can't do that with time. You can only go in one direction. That's a little bit weird. But that makes time a special direction. And you can work on theories in physics where you introduce more dimensions into space, like string theory. We have 26 dimensions or 11 dimensions or 10 dimensions, depending on what flavor of string theory you do. And some of these dimensions can be time-like. And by that we just mean that the dimension behaves like time, meaning that you can only go in one direction, and meaning that if you can prove that your equations let you travel back to the exact same point, then you've got a big problem with your theory, because that would be time travel. And so imaginary time is just like a way of, like at the complex plane, you have a real axis and an imaginary axis, if you remember high school math, perhaps. Then this is just a way of dealing with more than one time dimension in a mathematical way.
But that's the same thing as a two-dimensional object can't understand what a three-dimensional object is, right? Because it has
Yeah,
no tools to perceive how 3D actually is.
yeah, and there's like I think there's like is there a Brian Cox or a Feynman video about flatlanders on YouTube? It's pretty popular. It's basically this idea that what would it be like for us to perceive like a four-dimensional being?
I'm
So
going to keep on thinking about it.
You're gonna
yeah,
think
it's
about imaginary
I'm
types.
going to have a breakthrough. You watch.
exactly. I'm waiting
Yep.
for your contributions to
Yep.
science.
I'm pretty sure that it's like when the Enterprise needs to go at warp 6, it just goes to a different dimension where light travels at 6 times the speed of light in our universe. So
I'm
I'm all
actually
for it.
interested about this whole inflation discovery thing. Have you guys actually? I mean, have you followed this thing? Do you, as normal people, actually know that the discovery is being criticized and like how you say it's slightly uncertain whether they actually discovered anything?
It's the first time I've heard of it, so that answers your question, I guess.
I'm aware of the theory. I didn't know it was under any kind of controversy.
Yeah, it's interesting. There's basically this one. Oh, this is now physics gossip. This is good. There's a collaboration called the Planck collaboration. They have a big honking satellite in space, and the BICEP collaboration has a telescope at the South Pole. And so apparently, what happened was that at a conference earlier this year, one of the Planck guys showed a slide which he apparently shouldn't have shown at a conference. And the BICEP guys got a hold of the image of an image on the slide which showed like a little piece of sky that the Planck telescope was taking off sort of dust in the galaxy, and they used that slide or a picture of that slide to actually do what's called foreground reduction on their own data. And this is really not a good scientific way to do this stuff, and it leaves the possibility for them having completely messed up their analysis and this entire discovery not possibly perhaps being legit at all. And yeah, so there's some interesting stuff going on now, and yeah, it'll be interesting because Planck is going to basically confirm or refute this finding later this year, possibly before Christmas. And if they confirm this result, then it's questionable whether BICEP will actually get the merits of having just made the discovery. And it's a big brouhaha brewing.
As you guys know, I work in the news industry, which means that my job is to take information and make it really easily understood and repackage it so that people want to look at it for more than 20 seconds.
Food metaphors.
And that makes me the enemy of Timo, because what we do is we take things and we try to explain them without giving too much depth, and we usually end up screwing it up. So yeah, a lot of these things we try to say evidence for the Big Bang Theory because that's what's going to grab people's attention. And we can't go into the science. We're not going to publish a 50-page paper on what was actually discovered or not discovered.
I don't blame the news industry at all for this, because it was basically the biceps guy. If it turns out that they did like flub this a little bit, then that was basically them trying to get in on a huge discovery, basically Sherlocking the Planck guys out of possibly a Nobel Prize, and yeah, and I mean, and this is like these are big, huge international collaborations, and they have extremely strict codes of conduct. I mean, I can't. There's some colleagues in Helsinki I can't go to lunch with them because they basically talk about their work, and if they say something, I hear something and let it slip or something, then they will be kicked out of the collaboration, and Finland will be kicked out of the collaboration for that experiment. So it's and now I mean this is a perfect example of this, and I think it's pretty interesting. I really like to be the guy who showed the slide at that one conference.
Very good. Well, thank you, Timo, for explaining that to us as well as you could, considering our very low intellects here on ATW9K.
Oh no! You guys are absolutely amazing. I mean, this is one of my favorite podcasts.
Continue going.
Oh man, it's like, I mean, where should I start? Omar, he's such a handsome guy, and
Yeah,
Jason,
I know, right?
yeah.
Yep.
And
Now
Kevin,
I know he's lying.
always a suave gentleman, always such a good guy. Jason, absolutely superb host.
That's right.
And Ro is not here, so.
And that's why we love you right there. Yep. But for now, we're going to cut it short. We're going to direct you to go and listen to some other shows. They're not as good as us on Simply Syndicated, but they're there. They exist, I suppose. I'm just kidding, guys. All of our other podcasts that we love, Starbase 66, White Star 5 that talks about the Babylons. Let's see, what else is there over there, guys? For those about to rock, Do Ask, Do Tell. Lots of great shows over on simplysyndicated.com. You can actually catch up with those shows on iTunes or on SoundCloud. Hello, SoundCloud listeners. And that's going to be it for tonight. I suppose you could go ahead and follow us at ATW9K on Twitter and Facebook.com/ATW9K. That's Atomic Trivia War 9000 ATW9K.
And can I make one little recommendation? Is if you're following us on Twitter, if you have made it to this point in the podcast, we are very curious. So tweet us with the word, with the name J. Robert Oppenheimer. How about that? Robert Oppenheimer.
That's way too long.
Oh well,
Okay.
JRO. Let us know that you got to this point. You were a good boy and stayed to the end of class.
You can actually hash Timo. It was hash Timo.
Timo, that's nice.
I like
that
it.
way
You know,
we'll know.
hash has a connotation of fucking somebody in Finnish.
Oh.
Then yes, please.
It's drugs
please
over
hash-
here and it's sex over there. Interesting.
So, Hash, we're out of here tonight. Have a good one.
All right, cheerio.
Bye.
Bye.